Hello guys, and welcome back to Introduction to Number Theory. In this video, we will study the behavior of fractional part of n alpha, where n is integer number and alpha is an irrational number. So let me write this down. We'll study fractional part of n alpha, where n is integer, but we can consider it to be positive integer. So we'll write here arbitrary integer and also maybe positive integer. There is not so much difference between these two cases. And alpha is an irrational number. So alpha is not equal to any fraction of integers. Well, we understand that the fractional part always belongs to a semi-open interval from 0 to 1. So it allows us to consider not the semi-open interval, but the circle. This circle is made of this interval by bending it into a circle. So we can just imagine that it is not firm, but it can be bended. So we just take this segment and bend it so that 0 and 1 get to the same point. And alpha, actually n alpha, is like a grasshopper starting from this point and just jumping on this circle. So here we have alpha, and then we have 2 alpha, and then we have 3 alpha, and so on and so on. And when the grasshopper jumps over the beginning of this circle, where by beginning I mean this point here, origin of the circle, grasshopper jumps over this origin, it appears to be again on the circle as the fractional part when the number inside is greater than 1, appears to be again between 0 and 1. So this grasshopper is jumping along the circle, and all its steps, every its step, has the same length. Length we will denote also alpha. Well, of course, if alpha is greater than 1, then the length of the grasshopper's jumping is just the fractional part of alpha. The points where grasshopper meets the circle we will call marked points. So once again, the grasshopper starts from the origin of the circle and jumps, and the length of each of its jump is the same and is equal to alpha. And the points where the grasshopper lands on the circle are called marked points. So we will have several observations about these points. The first one of them is that the first observation is that all these points are different. So the grasshopper actually never returns the point where he has already been. So all marked points are different. Grasshopper never returns. Why is this so? Suppose there is a marked point such that the grasshopper visited this point twice. And he used n jumps And during these n jumps, he went through L loops to return to this point. So from the first visit of this point, during n jumps, he made L loops and returned to this point. Well, this means that n alpha is equal to L. So alpha would be equal to L over n, but this is not possible since alpha is irrational. So this is a contradiction which shows that the grasshopper never returns to points where he has already been. Second observation concerns the distance between marked points. Well, we understand that there are infinitely many marked points because the grasshopper never stops, is immortal, and we have infinitely many points. But how far are these points from each other? Well, the second observation is that for any positive epsilon, there will exist two marked points, I'll say here and here, such that we'll say what P1 and P2, marked points P1 and P2, such that the distance between these 2 points is less than epsilon. Where by distance, of course, we mean the length of this arc. Why is this so? Well, it is also rather obvious. Well, if we have infinitely many points, then let's just stop when the number of points, n, becomes greater than 1 over epsilon. So if we made more than 1 over epsilon steps, and we have more than 1 over epsilon points, and we have more than 1 over epsilon arcs between these points, so we understand that if every of these arcs were greater than epsilon, if its length were greater than epsilon for every of these arcs, so we have many arcs, and length of each of these arcs is greater than epsilon, well, greater or equal, and the number of these arcs is greater than 1 over epsilon, then the length of the circle itself would be greater than 1, which is of course impossible. We understand that the length of this circle is exactly the same as the length of this semi-open interval and equal to 1. So from this it follows that there are arbitrarily close marked points. If we want to find points such that distance between them is less than 1 over billion, we will find such points. If you want to find points such that the distance between them is less than 1 over billion, we will find such points. Okay, but the third observation is the most interesting one. It will follow from the previous 2 observations. The third observation is the following. Since we have close points, marked points such that distance between them is less than epsilon, then we know that from one point to another, the grasshopper needs some amount of steps to reach from one point to another. Well, suppose that from point P1 to point P2, he needs, say, k steps. What will happen if the grasshopper, when in point P2, makes another k steps? So from point P1 to point P2, let me show this on another picture. So point P1 and point P2, and it takes grasshopper k steps to move from P1 to P2. Okay, then alpha, 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 alpha. But what if the grasshopper takes another k steps? Then it will shift by the same distance, and it will get him into the point P3, where the distance between points P1 and P2 is exactly the same as the distance between points P2 and P3. And another k steps will bring the grasshopper into point P4. And another k steps will bring the grasshopper into point P5, and so on. And all these arcs will be just the same. Say L, 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 and so on. And if we choose L to be smaller than epsilon, then our circle will be filled with points, marked points, where density of these points will be such that the neighbor points are at distance less than epsilon to each other. From this it follows, our third observation, that for any interval I belonging to 0, 1, there will be a marked point inside this interval. So we can just write that there exists n, and at this point it really doesn't matter if n is integer or just positive integer, so I will write that there exists a positive integer such that the fractional part of n alpha belongs to this interval I. So once again, wherever this interval I might be on the circle, we understand that the density of marked points is such that there are such points inside I. What's more, there are infinitely many points inside I. Well, because if we take the previous k steps on and on, we'll keep getting into this interval I. Of course, we need to take epsilon less than the length of this interval. So in order to reach the interval, we need to take epsilon less than the length of this interval, and then apply observation number 2 and repeat k steps on and on. This statement is known as the Kronecker's theorem.